Welcome back to Numerical Methods, Episode 8 Lagrange Interpolation, the clean way to build the one curve through a set of points. A degree 2 polynomial looks like this. Three unknowns, we have 3 points, so we use them one at a time. At x equals 0, p is 2, the x terms vanish. So a0 equals 2. At x equals 1, p is 6. At x equals 2, p is 16. Packed into a grid, this system is called the Vandermonde matrix. Keep the grid in mind, we come back to it. For now, we solve the equations. The first equation gives a0 equals 2. Put a0 equals 2 into the second equation. a1 plus a2 equals 4. Put it into the third equation. Divide by 2. a1 plus 2a2 equals 7. Subtract the first from the second. a1 cancels, a2 equals 3. Back to a1 plus a2 equals 4. a2 is 3, so a1 equals 1. Put the three answers in order. a2 3, a1 1, a0 2. Check at x equals 2. 3 times 4 is 12, plus 2 plus 2, 16. Would this always work for any set of points? The determinant of Vandermonde grid is the product of all the differences, each later point minus each earlier one. No two points are equal, so every difference is non-zero. A product of non-zeros is non-zero. A non-zero determinant means exactly one solution. The polynomial exists and it's unique. So why not stop here? This way has drawbacks. 1. You solve the system, 3 numbers fall out, and you learn nothing about the curve. It is a black box. Secondly, for many points, it gets slow and the arithmetic loses accuracy. 3. Add one new point and you solve the whole thing again from scratch. We keep what it proved. The polynomial exists and it is unique. We build it a smarter way next. There is a second way to see uniqueness. We reuse this trick later. Suppose two polynomials p and q, both of degree 2, both through all 3 points. Subtract them, call it d. D is the degree 2 at most. At each point, p and q agrees, so d is 0 there. 3 zeros. A degree 2 polynomial cannot have 3 zeros unless it is 0 everywhere. If d is 0 everywhere, then p equals q. There is only 1. Now we throw away the system and build the polynomial directly, one point at a time. For each point, a block with value 1 at that point and 0 at the others. One block per point. Stitch them together and we are done. A small picture on the side tracks each block. Build L0. It must be 0 at 1 and at 2, so those are the factors. At its own point, x equals 0. Minus 1 times minus 2 is 2. We want 1, so divide by 2. That is L0. Check 1 at 0, 0 at 1, 0 at 2. On the picture, 1 at its own point through 0 at the others. L1 is 0 at 0 and at 2, so those are the factors. At x equals 1, 1 times minus 1 is minus 1. Divide by minus 1. That is L1. Check 1 at 1, 0 at the other two. Its peak sits at the middle point. L2 is 0 at 0 and at 1, so those are the factors. At x equals 2, 2 minus 1 is 2. Divide by 2. That is L2. Check 1 at 2, 0 at the other two. Its peak is at the last point. Same shape each time. On top, the distance to every other point. On the bottom, that same thing from its own point. Weight each block by the value it should hit and add. At x equals 0, L0 is 1 and the others are 0. The sum is 2, our first point. Same at every point. Only its own block survives, so the fit is guaranteed. Drop in the blocks. 2 over 2 is 1. 16 over 2 is 8. Expand the first. X minus 1 times x minus 2 is x squared minus 3x plus 2. The second. Minus 6x times x minus 2 is minus 6x squared plus 12x. The third. 8x times x minus 1 is 8x squared minus 8x. Collecting the coefficients. First of all, x squared. 1 minus 6 plus 8 is 3. For x, minus 3 plus 12 minus 8 is 1 and constant term is 2. So p is 3x squared plus x plus 2. The Vandermonde solve gave the same polynomial. 2 rows, 1 answer. Because there is only one. Two things worth checking. First, the three blocks add up to something simple. Here are the three blocks again, on the left. Add them together, unweighted. Watch the three curves stack up. A flat line at height 1 all the way across. Now prove it. L0 is x squared minus 3x plus 2 over 2. L1 is minus x squared plus 2x. L2 is x squared minus x over 2. Put all three over the same 2. L1 becomes minus 2x squared plus 4x. Collect the x squared terms. 1 minus 2 plus 1 is 0. The x terms minus 3 plus 4 minus 1 is 0. Only the constant is left. 2. 2 over 2 is 1. The blocks sum to 1 exactly. Here is the deeper reason. Adding the blocks interpolates the constant function 1. There is only one degree to interpolant, so the sum has to be 1. The second check is that if the points already come from a polynomial of degree n or less, interpolating gives it back exactly. We already proved why. The polynomial passes through its own points, so it is an interpolant, but there is only one. Take the cubic from our root finding series, x cubed minus x minus 2. Sample of our points and interpolate. You get it back untouched. The error is 0. Sometimes you want the value at 1x, not the whole polynomial. Neville's method builds that value up 1 degree at a time. Where it starts, the raw values 2, 6 and 16. Each one is a degree 0 guess, the flat line through a single point. Here's the rule. Each new entry is the polynomial that blends two guesses across two outer points. xa and xb are the two outer points. fa, fb are the two guesses being combined. Take the first two. Left point 0, right point 1. The guesses are 2 and 6. 9 minus 1 over 1. 8. That is just the line through the first 2 points. Now the last two. Left point 1, right point 2. Guesses 6 and 16. 8 plus 3 over 1, 11. Two linear guesses now, degree 1. Where it goes, blend those two lines. The outer points are now 0 and 2. The guesses 8 and 11. 16 and a half plus 4 over 2. 20.5 over 2 is 10.25. That value drops into the table. Degree 2. That single number is p at 1.5 and we never built the polynomial. Check against the full polynomial. 3 times 2.25 plus 1.5 plus 2. 10.25. 3 to try. 1 for each idea we built. Pause whenever you want. 1. Write the cardinal block L1 for the nodes x equals 1, 2 and 3. 2. Build the interpolating polynomial through the points 1, 2, 2, 5 and 3, 10. 3. With Neville, find the value p at 2.5 for that same data. Pause here, work all three, then check yourself. 1. Numerator is x minus 1 times x minus 3. The denominator works out to minus 1. 2. Those points come from x squared plus 1, so the interpolant is exactly x squared plus 1. That's the reproduction property. Number 3 is the table climbs 6.5 and 7.5, then blends to 7.25, matching x squared plus 1 at 2.5. We can build the one polynomial through any set of points and understand every piece. One catch remains. Every block is tied to the whole set of points. Add one new point and every block changes. You rebuild everything from scratch for data that keeps arriving. That is a real cost. Next time we fix that. We build the polynomial one degree at a time, so a new point just adds one term, that is Newton's divided differences. See you there.